All right, well, let's get started for today. We're shifting gears today. We've finished now talking about aromatic chemistry, and so now we're going to start talking about organometallic compounds, which is a very brief section. It probably won't even take the whole lecture. And then we're going to move into alcohols again as a functionality. We talked a little bit about them last semester, but we'll get into a little more detail about them this semester. So we're going to start today's lecture, as I said, talking about organometallic reagents. And I put up here on the board that the organometallic section of the lecture is coming from chapter 10 in your textbook, starting on page 215. And then when we shift into the alcohols as a functional group, we're going to be going into chapter 14, just to let you know that for a reference. Okay, so organometallic reagents. You may remember back in September when we started the course, we talked a little bit about the different disciplines in chemistry, and we talked about bioorganic and some of the bridging disciplines within chemistry, and organometallic reagents kind of fall into this area because they're organic reagents, but they contain metals, which is not a normal thing, and it's a little bit more of a definition than that, and that is that organometallic reagents have a carbon to metal bond. Okay, we've seen examples where we have, for example, an O minus with a sodium counterion. That's not an organometallic reagent because the metal is associated with an oxygen. Now we're looking at cases where the metal is associated with a carbon. And so the only example we've seen thus far in our lectures is this acetylide anion. If you remember from the end of last semester, where we could make this if we had a terminal alkyne, we could react it with a strong base like sodium amide, and it would give us this reagent. Okay, so this is in fact an organometallic reagent where something like this that we saw as a nucleophile when we talked about SN2 reactions, for example, this is not, because the metal is associated with an oxygen. Okay, so what's important about an organometallic reagent? What's important about it is it kind of reverses, as you can see, the normal reactivity we normally see with carbons, because we've seen, for example, a lot of cases where you have something like an alkyl halide, where the atom attached to the carbon is more electronegative. So we've been dealing a lot with electrophilic carbons. Well, in the case of a carbon being bound to a metal, now we're kind of reversing that because carbon is most likely more electronegative than the metal, and so you're having a different reactivity. Here the carbon is acting as an electrophile. Here it's acting as a nucleophile. So totally different reactivity. And you probably remember when we talked about the acetylide anion, it was acting as a nucleophile, right? Having the general schematic of this. And so in our discussion last semester, we were taking that acetylide ion and reacting it with alkyl halides. So remember, just as a reminder, we had the acetylide anion and we could react it with something like methyl iodide. And when we did this, that would act as a nucleophile, react with the electrophilic carbon of the alkyl halide, and we would alkylate. Remember, in synthesis, we use this all the time. It was a way of forming a new carbon-to-carbon bond. And we could have as many R groups in the alkyl halide as we wanted, as long as it was primary. We could add, as many carbons as we wanted. Okay, well, now we want to introduce how we could use that acetylide ion a little bit differently, because in this semester we're going to start talking about carbonyl compounds, probably in about 3 or 4 lectures. And so we want to go ahead and look at how an acetylide carbanon would react with a carbonyl compound. So something like an aldehyde or a ketone. And so as we would imagine, we're getting to the point now in our chemical careers where we can kind of predict what's going to happen here, right? Because I have this as the nucleophile, we already said, and so the other molecule must be acting as the electrophile, and so the electrophilic site in the ketone or the aldehyde is that carbonyl carbon. Therefore, we're going to have these electrons come in, form a new bond with that electrophilic site, and when it does that, it's going to break this pi bond and move those electrons out to the oxygen. So I can draw an intermediate after that addition occurs, right? Because I'm forming a new bond to what was the carbonyl carbon, pushing the electrons up to the oxygen, leaving my 2 R groups also like that. Okay? Once that intermediate forms, we can then just do a simple acidic workup where this oxygen pulls the proton off of the acidic water, and you end up forming the product, which is going to be the alcohol. And so you can see we're beginning to transition into alcohols here because this organometallic reagent reacting with an aldehyde or a ketone gives me an alcohol. Okay? And so what are some other Grignard reagents? What are some other organometallic reagents besides the acetylide anion that we could classify as organometallics? Okay, the first of those is going to be organolithium reagents. So as the title says, this is going to be where we have carbon attached to lithium. So it's an organometallic reagent because the carbon is bound to a lithium. And the way that we make these reagents is important. If you're, most of these organolithium reagents you can buy, but sometimes you have to create them. And how are they created? You take an alkyl halide and you react it with 2 equivalents of lithium metal. And the result of that is that you form this salt, where one of the lithiums is associated with whatever the halide was in the alkyl halide, plus you form this compound where you've associated the metal with that carbon atom. Now this in itself is an organometallic reagent, but usually not one that we tend to use because we then go on typically to take 2 of these organolithium reagents and we treat that with a copper iodide. Okay, and that results, and notice the stoichiometry. I'm using 2 equivalents of this to 1 equivalent of the copper iodide, and I form this product where I have 2 of the alkyl group, whatever the R group was here. I have 2 of them associated with the copper and the lithium. Okay, this reagent right here is an organometallic reagent, and it contains lithium and also copper, but it contains lithium. And this is actually called a Gilman reagent. And we're going to see later on how Gilman reagents can be used in reactions because, again, organometallic, its reactivity is equivalent to an R minus. So whatever the R group is in here, its reactive equivalency is behaving as an R minus, an R nucleophile. So this is the Gilman reagent. Yes, it's back in the days when they would name something that you developed after the discoverer, which they don't do anymore. Okay, now hang on, let me get back to where we were here. Okay, so the next organometallic reagent we want to talk about is one that's very commonly used in organic. Because again, any reagent that can form carbon-to-carbon bonds is important. And this next reagent is called a Grignard reagent. And it's basically formed by taking, again, an alkyl halide. So just about any R group you want to use and any halide is going to be possible. So you can have, your X can be Cl, Br, or I, and your R group can be primary, secondary, tertiary. So there are no limitations like with the acetylide ion. You can have primary, secondary, tertiary. It can be aryl, meaning that this could be a benzene ring with the halide on it, or it can be vinyl, meaning that this halide is on an sp3 hybridized carbon that's part of a double bond. So the diversity of R groups that you can use to form a Grignard is almost limitless. And to form this, you're going to react it with magnesium metal. Grignards require magnesium metal. And you're going to react these two things together in ether. And what happens is you basically insert the magnesium between the halide and the alkyl group. Okay, and so you have in effect then formed a bond between the metal and the alkyl group. So it is an organometallic reagent called a Grignard. Now you can already see that you want to get straight the difference between these two organometallic reagents we just talked about. One's called a Gilman and one's called a Grignard. Unfortunately, both starting with the letter G. Okay, but like any organometallic reagent, a Grignard, its reactive equivalency is R minus. It's a carbon nucleophile. Okay, so how is it going to react with other molecules? Well, let's look at the carbonyl compound that we did with the acetylide. And so we're going to take a ketone or an aldehyde, and we're going to react it with a Grignard reagent. And we're just going to, again, use just the very general, we're not identifying the R group or the X. So just in general, this reagent, what's going to happen? R group is going to behave as a nucleophile. It's going to come in and react with the electrophilic site in the ketone or the aldehyde, which is that carbonyl carbon. And when it does that, it's going to go through an intermediate, just like we saw with the acetylide anion, because basically it's an addition. And so whatever the R group is, and I'm going to put a prime on that R and put a prime on the R there so we know that's the one that comes from the Grignard. We're going to form this now tetrahedral intermediate because, you know, we went from sp2 hybridized carbon here to sp3. And then that we can then treat again with an aqueous acid workup where we simply are protonating that oxygen. And so we're forming what? An alcohol. Okay? If you look at this from the standpoint in general when you're dealing with carbonyl compounds reacting with the Grignard, you notice that it forms an alcohol. But what kind of alcohol? Well, let's look at the different cases of carbonyls that are either ketones or aldehydes. So in general, if you have formaldehyde, which is the simplest aldehyde there is, because it doesn't even have an R group. If I were to take that and react it with a Grignard, followed by an aqueous acid workup, it's going to form a primary alcohol. And how do I know that? Because basically when the R group reacts with that electrophilic site and kicks the electrons off and then is protonated by the aqueous acid, what is actually going to form? It's going to be R prime and then C, H, OH, H, H. Right? These are the two H's that are on the carbonyl. This is the carbonyl compound. This was the carbonyl oxygen, which is now protonated. Okay? And so using that same logic, if you have any normal aldehyde where you have an R group connected to your carbonyl carbon and then have an H, under the same conditions where you first treat it with the Grignard and then second with the aqueous acid, now you're going to form a secondary alcohol, right? Because now I'm going to have this R group and this R group from the Grignard attached to what was the carbonyl carbon. Same logic then if you have a ketone. And you react it under the same conditions, I'm going to form a tertiary alcohol. It's considered an addition reaction, so the formation of an alcohol from addition of a Grignard reagent to these different carbonyl compounds that are aldehydes or ketones. Okay? So what happens if I change the carbonyl compound? I'm going to change it to ester or acid chloride. Still going to use my Grignard reagent, but I'm going to do the reaction and see what happens. Because remember, with ketones or aldehydes, when I use the Grignard reagent, I only got alcohols. They're either the primary, secondary, or tertiary alcohol. It was an addition. I added the R group from the Grignard and formed the alcohol. Well, now we're going to take a Grignard and we're going to react it with, and I'll show you first with an ester. Okay? And so what's going to happen is exactly like what we saw before. This is going to act as a nucleophile and it's going to react with the electrophilic site in the ester. Well, the electrophilic site, remember, is right there at the carbonyl. So I'm going to react there, forming a new bond between this R and this carbon, and that's going to kick these electrons up to the O. And so the intermediate that I'm going to make is, again, going to have the two substituents from the ester, and then this is where the R from the Grignard has added. Okay, so everything looks the same to this point, okay, but something different happens here. Remember, with a ketone or aldehyde, I had R groups or R groups and an H, nothing that would constitute a good leaving group. Here, these electrons could come back in to reform the carbonyl. And when they did, it would displace the OR. Because remember, OR groups from when we talked about SN1 and SN2, these are good leaving groups. And so the result is a little different now. because now I have reformed my carbonyl, right? And I've lost that OR group from the ester. So I've in fact formed a ketone. Okay? Now who notices then something that might be an issue there? I've reacted the Grignard with the ester, and it's done a different reaction. It first did an addition, but then it substituted. So the substitution product is basically now this R group from the Grignard has substituted for that OR, right? So this is a substitution reaction. But now that this ketone is formed, what's going to happen? Okay, I'm going to redraw that ketone. So I'm redrawing the same ketone. Which is right here. Now what's going to happen? Well, if I have a Grignard present, which I do, what's it going to do? Nucleophile is going to react with the electrophilic side of the ketone, kicking these electrons up, forming this intermediate, where I've added the R group from the Grignard, and I have that intermediate. Now, oh, but I can move these electrons back in, right, and have a leaving group? No, because now these are all R groups. None of these are a good leaving group. So now, when I do the acid workup, I pull the proton off of the acidic water, and I end up forming this alcohol. And notice, it's an alcohol, and it is a tertiary alcohol, because I already had an R group on the ester, but I've essentially now added two equivalents of the Grignard reagent. So there are two alkyl groups that came from the Grignard that have added. Okay, so that means that the Grignard reagent adds twice to the ester, giving the alcohol product. Same thing will happen for the same reason if you were to start with the acid chloride. So let's go back and say, let's start with the acid chloride. If I react that with a Grignard, then remember, carbon's going to be the nucleophile reacting with the electrophilic side on the carbonyl, which is this carbonyl carbon, which breaks that pi bond and moves the electrons up to the oxygen. And so I initially go through this intermediate. I went from sp2 to sp3. I have the carbon from the Grignard adding, and so I have this tetrahedral intermediate. But now these electrons can close back in. Why? Because chlorine is a good leaving group. And so I end up forming, after one addition of Grignard, I form that ketone. And then what happens with the ketone? A second equivalent of Grignard reacts. Okay? So, quick summary, aldehydes and ketones, one equivalent of Grignard adds and you get an alcohol. With an ester or an acid chloride, two equivalents of Grignard will add and you end up forming the alcohol. All right? Now, there is a kind of synthetic utility reaction based with Grignards that I'd like to show at this point because, again, it's going to form an alcohol, and that's what we're transitioning to. If you have ethylene oxide, which you might remember from last semester is an epoxide. Remember we made epoxides when we used that peroxy acid on alkenes. We formed these epoxide structures. Well, ethylene oxide is just the simplest epoxide you can have. And it will react with Grignard reagents. Okay? And when it reacts, you form alcohol. How? Because this, remember, is a nucleophilic R group, reacts with the electrophilic carbon in ethylene oxide. It doesn't matter whether it adds to this side or this side because they're equivalent. And when it does that, it breaks this bond and moves the electrons out to that O. And so initially what I form is whatever the R group is from the Grignard, and then I have the two CH2s that were in the ethylene oxide, and then I have O minus, right? Because I've moved the electrons out to that. So close my brackets, react this with your aqueous acid. You're going to protonate that oxygen, and I will end up with this primary alcohol. But what's also true, it's a primary alcohol, but I also have added 2 carbons to whatever the alkyl group was on the Grignard. Okay? And so the Grignard reagent, as we can see, is very useful. Reactions that form new carbon-to-carbon bonds are very useful synthetically. And we've seen several examples of this now. But there are some limitations. So let's say limitations to Grignards. So there's certain situations where you can't use them. And the only one that we really need to know is that it won't work with acidic protons present. And so that means if you have, for example, an alcohol already, and then you're trying to add a Grignard reagent to it, won't work. Also won't work with carboxylic acids. Those are the 2 main cases. And if that's the case, it acts as a base instead of a nucleophile. So for example, if you had a Grignard reagent and you reacted it with a carboxylic acid like this, then what the R group is going to do, it's not going to react with the electrophilic carbon and the carbonyl. It's going to take off the proton, the acidic proton, and so you're going to end up forming the alkane plus the carboxylate. So you're going to make this alkane. Same thing if it's an alcohol. So this is a limitation, but what we always say, it can also be used to your advantage because, you know, if you have, for example, an alkyl halide and you want to get it to the alkane, you could do this. You take this and you convert it to the Grignard, and then you react it with a carboxylic acid, it doesn't matter which one, and you're going to actually get back to the alkane. So you're getting rid of your X. Okay? So you can use that to your advantage. Okay? Now, I mentioned synthesis and synthetic utility. Let's look at how we could recognize a situation when we could in fact use a Grignard for synthesis. Okay, and so remember, these Grignard reagents reacting with carbonyl compounds are always giving us alcohols. So if you have an alcohol as your synthetic product, then one of the tools in your arsenal is to think, well, I know that Grignard reagents are able to add with carbonyls, let me make that the methyl group here, are able to add to carbonyl compounds and give me alcohols. Okay, so this is in fact a tertiary alcohol. So the question we're asking is, how can I make this compound from some carbonyl compound and a Grignard reagent? And so to do that, what I'd be looking at, right, is these are the 3 R groups. So one of these things is going to be the Grignard reagent, and the other 2 are going to be part of the carbonyl compound. So looking at this being tertiary, the easiest thing would be to say, well, maybe I'm adding this R group as the Grignard, and if I did, it would be a ketone that I was adding it to, right? So retrosynthetic analysis would say if I started with this ketone and then this is my Grignard, and let's make it the bromide. If I added these 2 things together in the forward direction, I would form this product. Okay, but is that the only disconnection you can make retrosynthetically? No, because I could also say, well, what if this methyl group was the Grignard? And if that were the case, retrosynthetically, going backwards, I would go to this ketone plus this Grignard. Okay, and so which one of them is better? Which method? Well, it turns out that they work equally well. And so how would you make your decision? You probably just say, well, is this Grignard something I can make easily or buy? Is this Grignard something I can make easily or buy? The answer in both cases is yes. And are both of these ketones readily available? Yes, but this one is really available. Do you know what that one is? That's acetone. Now you could go into the lab and just squirt some in your reaction vessel and away you go. So this might be, from a financial standpoint, the easiest one, but from a chemical standpoint, they both work equally well. Okay? And so I almost said, are there any questions? Because I'm so used to saying that. But I'm sure there will be in our session tomorrow. All right? And so that's how Grignards can be used. And so now we're kind of transitioning from organometallics now, and let's start talking about alcohols. And so we've kind of transitioned now into chapter 14, because that's all we want to say about organometallic compounds right now, although we will revisit them. Okay? And so when we talked about alcohols, in the last semester we did talk about nomenclature, but I just want to remind you a few things about them. There are 2 common alcohols that we'll use a lot. One is methanol and one is ethanol. And methanol is, formed by basically distilling wood chips. And so it's sometimes called wood alcohol, if you've ever heard that term, wood alcohol. And, we use it as a solvent often, but it's kind of a dangerous one to use because it is toxic and it causes blindness. And so, it's used when necessary. Ethanol, on the other hand, is made from fermentation. And so if you take a sugar, all sugars are the hydrate of carbon. For each carbon atom, there is a water molecule. So it's the hydrate of carbon. That's why they're called carbohydrates, if you didn't know that. And then if you take this sugar and treat it with yeast, you will form, and I'll use the proper stoichiometry, you'll form 2 equivalents of ethanol plus 2 equivalents of CO2. And some of you may have, experimented with fermenting things, and you notice that there's always CO2 that's formed. If you've ever made beer or wine, there's always a bubbler on top to release the CO2. But this is how ethanol is produced. Now, The thing about alcohols are important before we get into how you form them and what kind of reactions they undergo is the fact that alcohols are versatile in terms of synthesis because, like water, they have a dual nature. They can behave as a Lewis base. So they have both, as we'll see, acidity and basicity. So they can act as a Lewis base, and that's where if you have an alcohol, you can treat it with a acid and form this oxonium ion, okay? And this actually is reactive towards nucleophiles. And so what you have to pay attention here is the alcohol is acting as a Lewis base because it's going to pull a proton off of the acid. So it's behaving as a base. But what it forms is actually electrophilic, because now this product that is formed, this protonated alcohol, remember, is a good leaving group. So when you have a nucleophile, it will come in and react with this electrophilic carbon now and displace the water. And it's a way of allowing nucleophiles to react with that R group. And I'm going to complete to balance that equation. Now this is nothing new. We learned this last semester. Remember how many times we had reactions where you protonated the OH and then it left as a leaving group? There are a lot of examples of that we have seen already. But it's behaving initially as a Lewis base, forming a reactivity where it's able to accept nucleophiles. Now, in the same way, because it has a dual nature, you can imagine it behaving as a Lewis acid. And when it behaves as a Lewis acid, that means it's going to interact with bases. So here is my alcohol, and I'm going to react it with a base. And I'll just use the generic B minus. And so this is going to come in and pull off that acidic proton on the alcohol and kick the electrons to the oxygen. And when I do that, I'm going to form RO minus, right, plus HB, which we don't care about. And so what I've formed here, remember, is an alkoxide. And we talked about these last semester. These are nucleophiles. And they're strong nucleophiles. All right? So you can convert an alcohol very easily into a species that is electrophilic or a species that is nucleophilic to use in a reaction. Okay, and that's the direction that we're moving in now. Okay, and so remember, with any new functionality, we've already talked about nomenclature. That was last semester. Okay, and so before we get into the reactions of alcohols, first thing we want to do is talk about how you can actually make alcohol. So preparation. Okay, now the big advantage we're going to see here is most of the reactions that we're going to talk about that you use to prepare alcohols are reactions we already know. This is all review. Okay, so for example, and I will actually label these as review to remind you. If you don't remember, go back and review them from Organic 1. So I'm just going to kind of present them. And the first is you can form alcohols using nucleophilic substitution. Okay? And that would be where you have an alkyl halide. And I'm just going to use a generic one because this is review. Let's make it a primary. And I'm going to react it with the nucleophile OH minus. Remember, nucleophile is going to come in and attack the electrophilic carbon in an inline mechanism. If it's SN2, it's going to kick off the leaving group like that. And I'm going to form the alcohol. Okay, so substitution reactions can easily form alcohols. Okay, the next review reaction is basically hydration. And hydration is where you're adding a water across a double bond. You're adding H to one side and the OH to the other. Remember, there were two different reactions that we learned that did that hydration, because you certainly can use H3O+, but remember we talked about the fact that that wasn't very versatile. So there are two ways that we talked about you could do it. Does anybody remember them? Oh, good, right. First one was oxymercuration, and that was where we reacted this with mercury acetate, remember, and water. And then you followed that up with sodium borohydride. So it was a two-step process. And that's the one that added water across the double bond, but it added it in a certain way. Okay, regiochemically, it added Markovnikov. Stereochemically, it added anti. Good, you remembered that. And so that would mean the result of this would be that the OH would end up on the more substituted side of the alkene. And this would be my alcohol product. But we also learned that you could use hydroboration, where you used BH3, right, and THF as a solvent. And then I followed that up with OH minus, water, and peroxide. Hydroboration. It added water across the double bond, but in terms of regiochemistry, it was non-Markovnikov. And in terms of stereochemistry, it was syn. So these are complementary reactions. So the result of that then is that the methyl group, methyl group is here. The methyl group and the OH are on different carbons because the OH went to the less substituted side. H went to the most substituted side, and they added syn. So just to help you remember, the water's adding syn, so I'll put the H in there. So you can see the water added syn, and that caused the trans arrangement of the substituents. So again, that's review. So we know how to do that already. All right. So now some new ways of making alcohols. So this is no longer review. The second way you can do this is reduction. Number one was the review methods. So reduction. Ketones and aldehydes can be reduced to give alcohols. And so basically, the reaction that's occurring, and this is my generic ketone or aldehyde, and I'm going to switch to a different marker because this marker's starting to run out of ink. Hopefully this one works. Yeah. And so I'm going to react this with some reducing agent. And the reducing agent, we abbreviate that with an H in brackets. That's a reduction. And just up here, I'm just going to show you, if we were doing an oxidation, we would use an O in brackets, but we're doing a reduction. So generically, H in brackets means reduction. And you will reduce this then to the alcohol. Now, does anybody recognize this as looking similar to something else? This looks like what was happening when we were doing the Grignard reagent reacting with the carbonyls, right? Because we had an aldehyde and a ketone, and we got an addition product, which was an alcohol. Yeah, this is basically the same reaction, except now it's an H we're adding. Okay, but the result is really the same. So we're going to see that reductions work exactly like that Grignard reagent did. Okay, and so if I were to call this aldehyde or ketone A, okay, if A is a ketone, then you're going to get a secondary alcohol. If A is an aldehyde, you're going to get a primary alcohol. And that's just whether this is an R or an H. Okay? Now, that reduction looks okay, but what reagents would you use that will qualify as reducing agents? So what are the common reducing agents? I may have to switch to purple. Common reducing agents. So what reagents, when treated with the aldehyde or the ketone, will give the alcohol? First one we've seen before because we've used it in lab. Remember when we reduced the ketone in lab? Sodium borohydride. And you usually use that in water, right? And sometimes with ethanol as a solvent, but sodium borohydride is the common reducing agent. Also, lithium aluminum hydride, which is sometimes abbreviated LAH. You'll see it written both ways. And then you have sodium cyanoborohydride. Gotta get my stoichiometry right there. And then, of course, you have H2 with a catalyst, but it's a little different than these top three. So I'm going to put an asterisk by it because even though it is a reducing agent, it's a little different in the way it behaves. But notice when I went through these, sodium borohydride, lithium aluminum hydride, sodium cyanoborohydride. All of these are hydride reagents. And so what's important about their reactivity is that they're hydrides. But we're going to see that these two are the most commonly used. And they have a little different reactivity sometimes, and sometimes they react identically. But one thing I'll mention kind of from a synthetic standpoint, if it's something that you're using in the lab, the main difference between these two is sodium borohydride is a powder. Remember we used it. You can scrape it out of a bottle and weigh it. And it's pretty, simple to use. Lithium aluminum hydride is always in a solution, and it's very flammable. And so when you use it, you have to be careful, or you can, in fact, easily start a fire. And so when you're choosing which of these to use, that's something that you may want to keep in account. All right, so those are the common reducing agents. And so basically, how would we use those with some specific examples? Let's say we have this aldehyde. And I'm going to treat it with sodium borohydride, followed by an aqueous acid workup. Okay? Now in a second we're going to look at that. But remember I said that this is, similar to the reaction of a Grignard with a ketone or an aldehyde, because I'm using a nucleophile and it's going to add. And when it adds, I'm going to need to have something to protonate that oxygen.
Okay, but the result of this, just from a general standpoint, is this. I've added an H to the aldehyde, and so I end up with that primary alcohol. Because remember, aldehyde reduced with the hydride gives primary alcohol. How is that occurring? And by the way, this would be how the reagent reaction would appear on your flashcard. Okay, so how is this happening mechanistically? Okay, these are all hydride reagents, we said, and we've talked about this before, where we talked about the difference between a proton, hydrogen, and a hydride. Hydride is where the hydrogen has 2 electrons. It has, a lone pair, so it has a minus charge, and it behaves as a nucleophile. So that hydride, just like we saw with the Grignard, this hydride is a nucleophile, so it's going to come in and react with that electrophilic side of the carbonyl. And when it does that, it's going to push these electrons up to the O. I hope you're recognizing already that we've talked about a couple of reactions that have, now we're seeing the same mechanism. So always keep in mind that situation when you're looking at the big picture. And so the result of that is going to be, I've pushed my electrons up to the oxygen, and now that H has added and formed this tetrahedral intermediate, sp2 to sp3. Okay. Now, could those electrons move back in like we saw with an ester or an acid chloride? No, because these are R's and H. Nothing's a good leaving group. So then all that happens next is when I do the aqueous acid workup, I'm protonating that oxygen, and so I end up forming the alcohol product. Okay? And so that's how all of those reducing reagents work, on whether it's a ketone or aldehyde. Mechanistically, that's how it occurs. Really the same thing that we saw when a Grignard reacted with a ketone or an aldehyde. Okay? And now, remember the asterisk in the common reducing agents. Again, this is a review, because we talked about this when we talked about aromatic chemistry. You can use hydrogen gas and a catalyst to reduce a carbonyl, like a ketone or an aldehyde, but only if it's in the benzylic position to an aromatic ring. That is the only case, and that's why it has an asterisk. And it also doesn't follow the same mechanism. Remember, this is review. We saw this when we were talking about aromatics. So that's how the H2 can reduce. But also notice that it doesn't reduce to an alcohol. It reduces all the way down to an alkane. All right. And so let's look at some more examples of this. We want to make sure you get enough examples. Here's a specific case. It's a ketone, and I'm going to react it with sodium borohydride, followed by the aqueous acid workup. And so the result of that is going to be the reduction to the alcohol. Okay? I'm going to pause here for a second. And we could also, we've seen an example with an aldehyde. This was an example with a ketone. Okay? But there is a special case we want to look at. If you have alpha beta unsaturated, ketones or aldehydes, then you have a special situation. Okay? Now, all of the reducing agents that we put on that list, with the exception of H plus catalyst, will reduce aldehydes and ketones to alcohols. Okay? But when you have alpha beta unsaturated, ketone or aldehyde, you can have some different reactivity. And so let me show you with a simple example. Now, alpha beta unsaturated. This is the alpha position, this is the beta position. We've talked about that positional nomenclature before. You know, when you're moving away from some object, if it's or some substituent, if it's once removed, it's alpha to it, and we especially use that in terms of carbonyl carbons. So, you know, these are both alpha positions. These are both beta positions. Alpha, beta, this would be gamma, you know, etc. But if it's alpha beta unsaturated, what that means is there's a double bond between the alpha and the beta position, because that's what makes it unsaturated. Okay, so alpha beta unsaturated means double bond between the alpha and the beta position. And when I have that situation, my reducing agents don't behave exactly the same. So I can have sodium borohydride and aqueous acid, and what I'll form here is what you would expect, which was simply reducing the carbonyl to the alcohol. But I also have some product where the double bond has been reduced. And it's actually about 60% to 40%. So that's a pretty significant mixture. And so what does that mean basically? That means that sodium borohydride does not work to reduce this carbonyl well if there's alpha beta unsaturation. However, lithium aluminum hydride followed by aqueous acid workup, it will reduce very specifically the carbonyl to about, I think, 95%. So if you have an alpha beta unsaturated ketone or aldehyde and you want to reduce the carbonyl, you should use lithium aluminum hydride. Sodium borohydride does not work well. Okay? Now, next thing to look at in terms of reduction, we've been talking about aldehydes and ketones. What happens if we have esters and carboxylic acids? Now I know we're getting to the end of this lecture because Austin's going crazy jumping up and down. I'm going to do a little bit of foreshadowing like I always do, so we'll kind of start at this point next time. But you notice that we broke this down by aldehydes and ketones in the reduction, and now I'm doing esters in a different category. Remember, we did the same thing with Grignards reacting with carbonyl compounds. And so now we're doing the same thing with hydrides. And so that's telling you again that mechanistically these are behaving the same way. And so I'm just going to show you. If I have an ester, and we're going to pick up right here, and I treat it with a reducing agent, I will form the alcohol, and it's always going to be primary. Always. Why? Because I'm adding two equivalents of H. Both of these are coming from whatever the hydride reagent is. Okay? And so just like with the Grignard, we always got tertiary because I was adding two R groups. Now with hydrides, I always get primary because I'm adding two H's. So we're going to talk next time mechanistically about why this is happening. We're also going to talk about the fact that now it does matter what reducing agent you use because not all of them are reactive towards esters and carboxylic acids. So that is where we will pick it up next time.